Did you see that?
Are you posting it just sometime in the morning?
All day Friday, yeah. And I'll try to build it before Friday and then do a timed release, so I won't forget. So, yeah. It's here online. There is a homework set for both today and Friday, and it's just more practice of these things. So, and I know they're long problems, so these will be up the value. All right, sorry, Duran, you gotta go away. I know, it does break my heart too. All right, so some of you have pin. That's what I understand. I have pin roller, so mine was fairly straightforward.
But then I worked it as a pin roller.
Okay, and I'm gonna work it as a pin. So I'm gonna first work it as a pin roller, like it is in the book. With your help, it'll go fairly fast. Yours is pin roller? Yeah. So just so you know, pin would set up 4 reactions. That's called statically indeterminate because we only have 3 equations. So it just means you're not gonna be able to just use the normal strategy to solve pin problems. They're much more difficult in analysis too, because you're not allowing the truss to expand. So thermal expansion and thermal stresses come into play when you have pin. Because it can't expand and contract. It's really cold out, it wants to shrink, it can't. So that creates internal thermal stresses that we don't normally have to deal with. Because if you let something expand, you create no thermal expansion. Okay, but that's a different life. That's next term's life. All right, so I'm gonna assume AY goes up. Is that true?
Yeah.
All right, what do we get for the reactions? AY. Come on, don't be shy. This is gonna save us time if you just throw me some numbers here. 12.5 K. Anybody agree with that?
Yep.
No? Nick's like, how about DY? 17.5 K? And those two should add up to 30.
Yeah.
Agreed?
Yeah.
And how did we get those?
Moment over A.
Moment about A. So the moment, I'm gonna write it because somebody didn't get these reactions and I wanna make sure we can get those.
Really funny. I got, because it's supposed to sum up to 30, right?
Yeah, 30 down.
I got 11.6 repeating and 18.3 repeating.
So yours does add up to
It does,
30.
yeah.
So you were like, oh, this should be good. All right, well, let's see what we get here. If I'm doing a moment about A, I have this 15 times 12. And that rotation is negative. This 15 times 24, that rotation is negative. I have dy times 36. That rotation is positive. And then I have 10K times 9. That rotation is negative. So that should be the equation that gives us dy equal 17.5. Comes out positive, so it does point up.
That exact same equation. I got it.
Okay, well, now I'm really interested. Yeah. 17.5. Calculator is not your friend.
How does that
How is that even possible? All right, so then AY is just going to be 30 minus 17.5 K, 12.5 K. So that's just our leave the truss together portion. We have not taken the truss apart. We're not doing joint analysis yet. We have to solve for those reactions first. Now we start to take it apart. AX definitely goes to the left. AY goes up. And DY goes up. So get those directions too. Confirm your directions. All right. Now we just need the joint analysis to solve this thing out. We want to stay away from joints that look complicated. B looks pretty complicated. 1, 2, 3, 4 unknowns. E looks fairly complicated. 1, 2, 3, 4 unknowns. F looks really simple. It says clean T. So when you see clean T's, they got to be clean. They can't have any diagonals coming off like this one does. That means that these forces all just transmit straight through, right? So these are definitely our friend. These are not our friend. I would never even go there. I'd go to A, F, I'd go D, C, and now I have pretty much everything except for this one. Right? And then I'd come here because I know that one, that one, that one. So kind of come up with a strategy, you know, when you attack these things, stay away from these. So I'll just go A first. Put in the knowns. Put in the unknowns, label them up. Oops. Whoops. 10K, this is AB, this is AF. Which way does AB go?
Right.
Maybe goes in.
AB has to have down effect,
Oh,
right? Because the 12.5 has up effect. Got to come down. And the component of AB is how much? The component of AB and the Y has got to be 12.5. So those kind of things you want to note if you can figure them out. Notice I didn't go to AF first and figure out that direction because you have 2 in the X that are unknown if you do this one first. So you won't be able to like just look at this and go, oh, AF goes, I don't know, because I didn't know what AB did, right? But once you learn for sure what AB does, now I know I have left effect, this has to be right effect. So look at those components in your brain and that'll help you. We need an angle. So I'll get this angle. That is inverse tangent 9/12. 36.8699. Theta. 36.8699.
that's the same angle on E also.
Yes, that is correct. This thing is symmetrical. Shape-wise, it's symmetrical, not load-wise. Load-wise, it's not symmetrical. That's why these two are not the same. Yeah, good. So now I need AB. So I can see that I can just build a triangle with the 12.5 and the angle to get AB. So that would be, there's lots of Valentine's activity on my phone. It's good when you have a family because they gotta love you, right? Sure. I guess they don't have to. All right, so here we go. I'm gonna use sine and opposite over hypotenuse, so sine of the angle. I'm just gonna write theta so I don't rewrite this thing over and over. But theta is equal to that angle. 12.5 over AB, AB, equals 12.5 divided by the sine of our theta. 20.833. Anyone get that?
Yeah. I got it.
Okay. Don't want to make any early mistakes.
Yes, and line, or AF, would be on the book in wrong, we talk about that.
Yeah, we'll prove it. Is this compression or tension?
That would be tension.
Careful.
Oh, it's heading to the point.
Yeah,
So
it
it's
goes
compression.
into the point. It's compression.
That's what I have.
So there's our first member. Done. Now we need AF. AF is gonna be the combination of the 10K, AF, and the component, right? All the forces in the X need to be considered. So I'm gonna write that some forces in the X has to be equal to 0. Cannot forget the 10K. Equals minus 10K, right? It's this one. Plus AF, that's this one. Minus, and this will be the cosine, right? So I'm gonna write it out just to make sure.
And
What
use tangent of that one. Right.
I'm gonna use cosine, it's adjacent for AB. So I just wanna write it out somewhere where I don't, all right, I'll write it out below. Cosine of theta, theta's known, 36.8699. And I'm just using this little component here of AB, right? So cosine theta is ABX over 12.5, ABX equals, I'm gonna crunch that number. 12.5 times the cosine of theta. Cosine 12.5 times, that's 10. Okay, so that goes in my equation, 10K. That's this little guy, this component of AB. It's not 12.5, you guys, AB is 20.833. Can't let me make those mistakes. There's no way this could be 10K. Cosine is 0.8 and 20.8 times 16.664K. That goes in here. 16.664K. So this is the component of AB. 10K going left, AF going right. That gives me AF equal to the summation, right? 26. What's the book get? Huh?
What number are we talking about?
AF.
I think it's the same number right here.
This is problem 5.3. 5.3, it gets AF at FA. How would I say? Yeah, 26.7. Same thing.
So I
So-
get that,
Did you forget the 10?
I missed the 10.
Yeah. Super easy to do. compression or tension, it is tension. All right, let's make sure everyone got what I just did, because that's super important.
Yeah.
When you're doing forces in the X, you have to consider all of them, and there's 3 forces in the X. There's 10, there's AF, and then there's the component of AB. Negative, negative, positive. So that's these. Negative, positive, negative. That's just one joint. Good times. Wait till it's pin pin, right? But this one you could do
Yeah.
if you found AY
Yeah.
correctly. So if this was a pin, we still could do this joint. There's a roller in my book right now, but if it was pin pin, you could still start here and get this. And then we're going to move to F. So this is joint F. And it's got 15 down and then AF coming away from the point. So AF comes away from the point and is equal to 26.6. You'd want to keep all the precision there. This is 15K down. This is FE. And this is BF. So joint F, super easy joint. Everything just transfers straight through. BF is 15K. FE is 26.6K. Everything in tension. Pointing away from the point. So we look for those in a truss. We want to move to them because we solve them pretty easily. So the diagram's starting to develop. AB is 20 point, I'm just gonna round 8. Compression. AF 26.7 tension, 26.7 tension, and then going up 15. Tension. So that means there's only 2 unknowns up here, although I'm not super excited about going there. I could, right? There are still 1, 2, 3 unknowns here. So my next strategy would be to jump to D if it was a roller, and it is right now.
Actually, myself, that's where I started and went back.
Yeah, no, you could start at D for sure and move left.
Yeah,
You could
that's
go D to C. Yeah, that would be completely appropriate. More than one way to solve a truss for sure. All right, so I'll do D. Which way does CD go? Definitely down. 17's going up.
Yep.
So it's got to have down effect. So I didn't do ED first because there's 2 in the X. I don't know which way they go. So CD, look at Y first. This has got to come down. That means this has to go left. When you have 3 forces at a connection, it does create a right triangle because of equilibrium. There's no resultant. it's gotta be in equilibrium. So all three of these forces do create a right triangle. So that strategy works if you have three. You cannot use that strategy though, if you have more than three, like right here, all these forces are not gonna create a triangle, right? There's just too many damn forces. When you have three though, it does create a triangle if you want. Instead of doing components, you could do force triangle. That makes sense? So if you see three forces, you're like, oh, I could draw a force triangle. So a force triangle for this one would look something like, and you gotta do them tip to tail, that's important. You can do them in any order, but they have to stay in position. See how I kept everything in position? So this becomes ED, this is 17.5, and this is CD. And we know the angle between CD and horizontal, that's right here. So you do have to pick out that angle correctly if you're gonna do a forced triangle. Don't muck up the angle, you muck up the problem. So this is our theta, 36.8699. Right, and then we can solve for those two, just with trigonometry. So this one would be the sine of the angle 17 over CD, that would give me CD. So that's gonna end up to be the sine of the angle divided by 17. If you need to, write it out. Sine. Remember theta is this 36. Opposite 17.5 over hypotenuse CD. So that's going to be 17.5 divided by the sine of theta. $29.17. Anybody get that? Good. And compression or tension for CD.
Compression.
Yeah, going into the point. That's CD. And then ED, same kind of thing, we'd go cosine over CD. Or you could use tangent. You get it? Because you know this one. Either way,
I like tangent because,
it doesn't use,
something that you already know.
Yep.
Not calculating.
we'll use tangent. I like it. ED over 17.5. Whoops, tangent of the angle is opposite over adjacent. I reversed them. 17.5 over ED. Remember theta is 36.866. So you got to swap those. It's again 17.5. And this time tangent. 23.33.
Yes.
Compression or tension.
Tension.
Yeah, it's pointing away. Tension. All right, ED 23.33. And it is tension. And CD is 29.17. And it is compression. Very hard to determine that stuff without like going through it. It's a little bit intuitive if we push here that this is going to be compression. It's not so intuitive that that's tension when you push here. But, and then across the bottom, we're tension, tension, tension. So we're close. We have 3 more to do. 1, 2, 3. C looks good. Go there. Only 3 forces. That's going to create a triangle. So joint C That notation's super helpful for me, so I know what is going on, right? And we know that this 29 is in compression, so it points in. Pointing in here. So that means BC points in to give us both opposite X effects. And that means that CE points away. So I'm just gonna go straight to the force triangle at joint C. So this is CE. This is BC. And this is 29.17 for the hypotenuse. If you see three forces, you can build a triangle. You don't have to do the component analysis. And we need this angle between vertical and C. That's right here, between vertical and CD. Right here, and that's gonna be right 90 minus the 36. You could use the 36, it's up here. Right? Either way. Yeah, that'd be this one down here. Correct. So I'll just keep using the 36, that's up here. So the 36 is here, and the way I look at that is horizontal to CD. So then I go here, horizontal to CD, it's right there. Those two on a equal opposite angles.
Wait, because you're finding the, wait, can you point to what angle?
So this angle here
Yeah.
is our theta. Right? That's the 36. And the way I look at it, it's horizontal to CD. That's this angle.
Yeah.
Agreed? Then I go to my triangle, I go, where's horizontal? Right here. Where's CD? Right here. That's that angle right there.
And which one is that? Big day.
That one. Theta. And theta. Where? What, how do I have you confused?
Like if you draw it like the regular. Like,
Yeah,
then that would be.
so the regular joint diagram would be like
BCD.
this, this, and this. That's the regular joint diagram, right? Agreed? This one here? Okay. So then it's theta is out here. Right? Theta. So this theta ends up out here.
Oh.
These are opposite, yep. So this would be the 50 whatever that was calculated. Yeah.
And you
Yeah.
said minus 90.
Yeah,
I mean, or you can.
you can use either one.
Either one
Works, just know which one you're using. This would be if I'm using the component method, right? I draw it this way. And that'd be like, oh, this is gonna be equal to the component of this, I would find the component of this. Triangle method would be just build the triangle and get your angles in the right spot.
But also find using the component given, which is 9 feet and 12 feet, and it's gonna be the same in
Ooh, I don't do ratios, but I get what you're saying.
but no, what I'm saying, you can find it in many ways.
No, I agree, totally. I wanna show you one, I'm not gonna show you many, because that just promotes confusion.
Yeah.
So. All right, so make sure either way that you do it, you get the angle in the right spot. Theta's up here for me. That's the 36. That's the one I'll use. So then like sine would be CE over 29.7. Right, so I could get CE by taking 29.7 times the sine of theta. I think my 36 is still here available, sine times 17.82 for CE. Anybody get that? Or did I muck that up?
Yeah, that's what I got.
Oh, good. And it points away. So it's in tension.
Hmm.
You can get that, Sean?
Yeah.
Oh, I probably do have rounding.
Let's see.
That's a lot of
what the book
rounding.
says.
I can't believe that. 17.5.
But we did it. We should some. Yeah, we did. I bet.
Let me do it again, because I did not round. I did round the 2917. Did you get 2917?
Yeah.
Did the book
Yeah,
for CD? Okay.
yeah.
So I don't know what that whole number is.
17.502.
Okay, 17.502, enter.
Where we got CD.
Okay, wait. I don't want to add confusion to me. Let me see what I get here. And now I really screwed it up. So hang on. What's the 29 number again?
9.17.
What's it not rounded? That's what I used.
1667.
1667. Thank you. And then the angle and sine and times. I get 17.5 when I don't round. Is that what the book gets? Okay. Now, one. I don't know if we actually need another way to do it, but if you want to add confusion, go for it.
Well, you told us the way we
We
did
got
it wrong.
CD by using the Pythagorean theorem to get it. So we said CD equals the square root of the hypotenuse squared minus the side. Well, we're not using BC there, we're using CD.
Okay, can't do it. No one will be able to follow that. Like if somebody, I get that it works. But you're gonna have to be able to write it down the way somebody can follow it. Like there's square root of something here, Pythagorean theorem, I can't do it because I don't know those two. But I get what you're doing. You're just carrying components over. But you gotta, however you do it, you gotta note it so somebody else can follow, like, what is going on here?
You're selfish.
I love it, though. It's a full comprehension of the translational effect is what it
Okay, so-
is. Like all the translationals work.
Just to clarify, on
Yeah.
Monday, you were like, you can't do this, and from my understanding, maybe I wasn't fully listening. I thought when you said you can't do this, you meant like,
It will never work.
yeah, it won't work. Like,
So-
we miraculously got the answer,
Yeah,
but are you just saying it's just confusing?
it's super confusing
Okay,
and super poor practice. Like any other engineer looking at your work is gonna go, what? How'd you get that? And so when they work and get the same number, then it'll be all joy. It's when they work and get a different number, then we can't just look at how you did it. It becomes a little bit confusing when you pull forces from another connection. I don't know if that makes sense or not, but
And what tension is on?
points away or it points into, which one?
Oh,
I have it pointing away,
Actually,
In
going
the-
down, so it's away from.
away from the connection,
When you join.
right? Isn't that one away?
that's what I did. but-
Yeah, because this one, you know. That carried over from D, right? So you know that one points in from your D analysis. So let's go to the D analysis. Yeah, that one points into the point. So then up here, it's got to point into the point. So if this one's up effect, this one has to have down effect. Tension, compression, compression. Excellent. What'd you get for BC?
same number as,
Which is
23.33. But, the directions are different. No, yes.
into the point,
But,
into the point,
for which one?
the one we're talking about, BC.
Yeah.
That's compression into the point, correct? Good times. Good times. So to get that from this triangle, it's gonna be cosine of the angle is BC over the hypotenuse. Again, it's a multiplication. So 29.17, we're gonna have rounding again. My angle and cosine and times. Yeah, I get 23.33. Actually 3.4, but that's because of my rounding, I'm sure. Whew, excellent. I would not encourage you to get it on one piece of paper like this. This is a little bit chaotic. Jumping around all over the place here. So it's not perfect, but it's good for the overhead projection to kind of contain it. Wow. What is the largest loaded member in the truss? Two of them. We're done.
We haven't done BE.
Oh, we do have one more to do.
Yeah,
Thank you.
no.
How do we get BC? The
BC.
little triangle.
Did you do it this way,
I
Gina?
just wanna do it that way.
Okay, so this and this, the component of CD have to be equal.
Oh. okay.
Agreed? So you
Okay.
just find the component of CD and that's gonna be what it's equal to.
Oh.
That make sense?
Yeah.
Okay, perfect.
What?
Where do you want to go to get BE?
Joint B. is
Joint
what
B, let's do it.
we just like.
Can't just draw a triangle.
We were grasping, we were really grasping.
That's good.
I don't know, like.
This is a battle that we need to win. There's my joint B. I'm gonna squeeze it in. So I know 10K is coming in. I know 20.8 in compression is also coming in. That's rounded. I know that 15 is coming away. I'm just kind of reading my force diagram here. I have no idea what BE is doing, but I know it's there like that. And then I have 23.383 in compression, and that's coming in. Right?
Yeah.
So you put in everything you know, leave the one that you don't know, and then try to figure it out. We have a bunch of X effect here. But we have some X effect here and some X effect here. It's really hard to tell which way that goes. If we look at up-down effect, there's some up effect in this one and there's 15 down. Again, I don't know which one wins. So I am unsure which way this goes. And that's okay.
How come you're not including the 17.6 out?
I draw a circle around this joint.
Oh, I'm looking at the wrong joint.
Yeah, and draw a circle around that joint. Everything I cut, I put in.
Got it.
Nothing else, nothing from any other joint. Just the stuff traveling to that connection. So what I say is, yes, you need to put a number in, direction wise for BE. Let's guess at which way it goes. My guess would be up. I don't know which way it goes. Maybe you do if you already solved it. But I'm guessing up. So that means when I collect my forces in the X and Y, I know which way it's going. I can put in a sign. If the solution to BE comes up negative, wrong direction. Flip it over.
Yeah, I
Okay.
thought BC goes to the right.
All right, BC is in what? Compression. So it points in to the point.
Both of them.
What do you mean, both of them?
Wait, how did you-
It points into the point here, correct? So then it points into the point here. It does switch.
Yeah.
But that's the way it works. You have to, that's what has to stay consistent. If it points into the point on one side, is it got to point into the point on the other side?
Never a point here.
Nope, that would make not equilibrium. So These two fight each other, right? If we just look at the member, then it's either this way or this way, and you can see that flips those directions. Yeah, yeah. Yeah, that'd be chaos. The poor member would be like, what is going on? All right, so here you're gonna either go, okay, I'm gonna sum forces in the X, or I'm gonna sum forces in the Y. Either one. In the Y, we have 1, 2, 3. In the X, we have 1, 2, 3, 4. I would say, oh, let's sum forces in the Y. There's only 3. That makes sense? You can do either one, both should work. And I'm gonna try to write it across the top. Sum forces in the Y. That means we want to collect everything going on in the Y. So we got 15 down. I'll do the easy one first. And then we have the 28, 8, and I need its Y component. So this angle here is the 56, right? Between 53, between here and here. This angle here would be the 36. So again, you got to dig these angles out. Make sure you transfer them up correctly. I'll use the 36. That's the theta. And I'm trying to find the Y component of the 20.8. The Y component is there. So that would be sine of theta, just looking at the 20.8, right? And I write it, the Y of 20.8 kind of thing. Somehow I note that it's a Y force of this. That's the thing I want right there. And it's over the hypotenuse of 20.8. So that's the 20.8 times sine theta. And I have rounding, so I don't, oh no, I got that number. Cool. $12.5 for this one. So this, the Y component of 20.8 equals 12.5 K. I'm using theta. We define theta in the very beginning as 36. You could use 53, but then you just got to use cosine. So either one. And again, just found the Y component that goes into the equation. It's going up, so it's a plus 12.5 K. So now I have the 15 in and that Y component. I need this Y component. The Y of BE. That would be the 3 forces in the equation. Just using the 53 angle.
Yeah.
Yeah, you can do that.
But then.
It's gotta be
what about
cosine.
16?
So 53 is here. Right? So it's gonna be cosine.
The,
No, this is theta up here. Because theta is between this and horizontal, between this and horizontal. So it's here and here for theta. So that's gonna be your 53. So to find the Y component, you're gonna have to use cosine because it's adjacent to it. That trig, man. It's rough. You have to just like be able to see it or draw the picture, which I'm not redrawing this force out here, you know, with this. That would be helpful if I had the space. If you're not sure, pull the force out and do the components, right? If you can't work with this kind of mess. Same with BE. I could pull BE out and do the components. I just wrote in BEY. That's the Y component of BE in the equation. Some forces in the Y. 15, 12.5, and this unknown, right? So in this case, I'm gonna solve for BEY. The Y component right there. Once I have that, I can get BE just from its own triangle. So BEY equals what? 12.5 and 15, they're opposite sign. The 15 moves over, yep. 12, 13, 14, 2.5. The 15 negative moves over, becomes positive. 12 moves over, becomes negative. We have a positive 2.5K for this. 2.5K, this little component. It came out positive, so the direction's good. My assumption of it pointing in is correct because this is correct. And when a component's correct, then your hypotenuse is correct. All right, so now we have one step left, and that's to solve this thing out. So if this is theta, horizontal to this is the same angle, this is theta. 9 and 12. 9 opposite 9 adjacent 12. Opposite 9 adjacent 12. So this is theta.
So, question,
So that's theta. Yeah.
so even though we have the 10K apply on at the B intersection.
Yep.
Junction. We don't use it in the equation.
Right here. Right here.
No,
10K.
no, but the equation, the
I'm
Y.
doing forces in the Y, not the
Ah,
X. This is
never mind,
X.
yes.
Yeah, yeah. So that's why the 15K is in there.
Yes.
Yeah. Super easy to get it all mucked up in your head. It's really easy to forget what you're doing. Like why, what am I doing here? I'm summing forces in the Y. So that helps remind me. So this is theta. My 2.5 is known. So I can say sine theta, that's the 36, is 2.5 over BE. BE is 2.5 divided by sine theta. .166. Anybody get that?
Yeah, but not doing that.
That's all right. That's okay. Do you understand that?
Yeah,
Okay, good. And it points into the point, so it is compression. Whew, that's crazy truss. Pretty typical truss. About the same number of members in a roof truss. It's a different style of truss, of a bridge truss.
Where did you sum the moments of X on the different? Just for what we just did. I can't find it.
Where did I sum the forces? Because I
Oh,
only,
did I say moments? Sorry.
yes, you did. That's all right. I was confused. So right here is where I sum forces in the Y. Right, so that's the 15. That's this component.
Right.
Here, and my unknown BEY.
Mhm.
This little Y component. So we've solved this BEY for 2.5, and I put it in right here.
Oh,
Then I just isolate BE because I know a component of BE and solved it. And that's what this little shenanigans is up here in the corner. Where I took the sine of this angle, which is opposite over hypotenuse. 2.5 over BE, then I solve for BE. These two switch places, 2.5 divided by sine theta. Yeah, the flow's not fantastic here, but. Whew. Money right there, we're making some money,
2.5.
huh?
How'd you get 2.5?
Right here, summing forces in the Y. 15, that's this down.
You can't just do like another component thing?
I just put, since you're summing forces in the Y, I put 15 down, right? I put that component going up because I could solve it. I know the 28, right? So I have a number there, but here I don't know BE, so I can't solve for it. So I just put in that component directly into the equation. Some forces in the Y, I put BEY. You could write this in terms of theta and BE. I find it more complicated for most of the folks to do that. So when I'm summing forces on the Y, I just put the component in, then find the component at 2.5, and then solve for BE. I think I know what you're saying, Gina, because you can put in the equation. You can put this equation in, solved for BE. It would be sine theta. It would be 2.5 divided by sine theta. And you can put that in there. But it's, I think, a little more complicated, but it's always hard to tell.
4.16. What you got?
4.16, yep, from this, yep.
Wait,
And it definitely points into the point because that component went up.
and then wait, I didn't get that again.
The 4.16.
Yeah,
So I know this is 2.5.
Up.
Right, up, correct. I know this angle is theta,
that's the 20.
36.
Wait, really?
Yes, ma'am.
Oh,
So-
right. Okay.
Yeah. Because the opposite side is 9, the adjacent side is 12, opposite side is 9, adjacent side is 12, it's gotta be
Oh,
the same
it's
angle.
equal- and- and
That
E
one,
is 53.
yes,
Okay.
yeah, that's opposite side is 12 and 9, so
So
that's,
then you just made that a triangle.
I made BE a triangle, yep. And then I solved for BE knowing an angle and a side,
So opposite.
yep. Sine theta, opposite over hypotenuse, yep, exactly. So just gonna say what Gina's doing is super important. She's trying to clarify what the hell I did. And if you can get that, it's money. What are we doing in an earthquake?
On the ground.
Get under the table, yeah, good. Run, run and dodge falling shit. That's a strategy, I think. Has everyone been in an earthquake? That they remember? Jorge has, I have. I was in the big Malala quake. Remember it very specifically. So my home is a ridge rafter home. It's not a truss home. I don't have a truss roof. I have a giant ridge beam that runs right down my home. And then I have these giant exposed rafters that go up to the ridge. And then on top of that, I have 2x6 roofing. And on top of that, I have 8 inches of rigid foam. That's the insulation. And on top of that, I have a metal roof, right? So from the inside, you see the giant ridge, the big rafters, and then the pretty ceiling. And then on top of that is 8 inches of foam. On top of that is a metal roof. Well, the foam is foil backed on both sides. So you have foil on both sides of your foam. So the very top layer is foil, rigid insulation, and metal roof. So metal roof right on the foil. So metal on metal. Does that make sense?
Mhm.
So when the house shakes, guess what? It is like being inside of somebody with a chalkboard and fingernails. Literally, it is just scratching. It was the loud, I didn't know I didn't even notice that I was moving. But I could just hear this sound of my house like coming apart or whatever. And it wasn't coming apart, it was just moving like it's supposed to move, and it was the metal roof on the foil just going like that. So loud, it's like, what is happening? Yeah, it was crazy. And then I was in the Portland one, that was way back, like, I don't know, 90s, early 90s, and that was a pretty good shake. And I remember looking at, you remember that one?
baby.
Oh,
My
well.
Parents left me in the house on.
Oh, nice.
What?
Did they leave?
They got out of the house.
Yeah, I got out of the house.
The other one
Yeah.
grabbed me.
2 out, 1 in, and they're just doing numbers. Right.
You fired them?
I remember looking, so when it happened, I was in my bedroom and I knew it was an earthquake instantly, like you could feel it. And I looked outside the window and the power line poles were like wagging like dog tails. It was crazy. I was like, wow, that's nuts.
Yeah, guys, you need to follow on. That one.
Let me tell you, when the 10-0 hits, we're all gonna feel that one, man. It's gonna be crazy.
I was born in Salvador, so the earthquakes every day.
Yeah, all the time. Like, it's like Southern California people, like.
Yeah.
What?
Now that I went back, there was the 4.2, I think.
Yeah.
I didn't feel it. My son was like, "Did you feel the earthquake?" I said, "No." You're in the hammock. It's called Hammock Valley. So it's earthquakes every day.
All right, here is the solution to 42. And Sean is gonna talk us through it.
All right, so you do.
Okay, thank you, Sean. Let's move on. All right, let's go pin on this one. We won't work the whole thing because that would be another hour. But let's get it started. So I'm gonna redraw it. And save some time on the recording. Resume recording. Okay, here we go. We've done a little work since you were all gone. We've done that. Okay. Went to F, then we went to A, jumping all over the place. Now we're up here at B. Yeah, all right, sorry about that. But that's all right. You want me to solve it again? We've done this one once, exactly like this, right? Exactly like it. It was here. So we ended up with 2333 for this upper force. I guess you can rewind it. If you look at the recording, you can rewind the back when we solved this. And then we came up with BE at 23.33 and no, 44.166 and BC at 23.33. Compression into the point and compression into the point. So that was from here. So once you have that, then you can kind of click along. You can move to here and get this, just like we did before. Once you have that, now you have this and this, you could go to C and get that, and you just continue to work around until you have everything except for these crazy X forces along the bottom. But once you get this, right, and you come down and get these two, you can get these. They become super difficult to get them. You have to get them last, very last. So pinned is pretty rough. I don't think we need to grind on it much more, because I'm not giving you pin in trusses. That is a typo. We're not doing statically indeterminate. We're gonna do statically determinate trusses. That's typically what we calculate. There's other ways to do this, and we will learn another method. It's called sectioning, where you cut the truss. So that would be one strategy here, like, oh, we could cut this thing and solve for one of these X forces. Because the X forces are gonna get, even though you know all of these, right, across here, if you don't know these, you still can't solve this. There's 2 unknown in the X. Here, you still can't solve these, even though you know that, right? So it's gonna become, you're stuck with the method of joints. You need this other strategy that we haven't even talked about yet. It's called sectioning. Okay. So, I mean, I can explain sectioning. We don't need to do it yet though, as far as practice it. But sectioning says, all right, you have a truss. The entire truss is in equilibrium. You can cut it. And then you can work with this side of the truss and leave this together. Right? So then you end up with a force here, a force here, and a force here. Yeah? And unknown here, known here, unknown, unknown, unknown. You still got 4 unknowns. It's still statically indeterminate, but you can start doing some moments to figure things out. So they're super hard problems. You'll do a moment, you'll get 2 unknowns, and then you'll have to do some forces of the x, you get 2 unknowns. Now you have 2 equations, 2 unknowns, simultaneous equations. It's like, oh my God, this is so hard. Just put a roller in, right? So yeah, we won't go there yet. Sorry about the pin, folks, who had pin. All right, let's move on. Your homework, let's all make sure that we have, and I'll do one more truss, but I just want to talk about homework real quick. You're gonna do 7 and 8. So let's see what we have for 7 and 8. Let's make sure they all look the same. Wow, what a concept. Chapter 5, 7, and 8. Yeah.
I'm gonna do the 8 using the method of joints.
Yeah, so 8 says, use method of sections, right? That's what 8 says. Oh, you can't see it. So first, let's talk about 7. 7's super long problem, right? A lot going on here. So what I want you to do is solve for these 3 members across the bottom. So make a note on that. I want CE, ED, and DF. Not the whole, you don't have to do the whole truss, is what I'm telling you. Just the bottom 3 members. Actually, we'll say 4. 1, 2, 3, 4. These members. Oops, focus. Focus. There we go. So what are they? It's CE, DE, DF, and EF. Do not have to solve for the upper 1, 2, 3, 4, 5 members. Just shorten it up a little bit. Sound good? All right, now let's look at this one. And by method of joints, I'll have you do these 3. EF, IF, and EI. And I'll put that in Blackboard for the folks that aren't here. I think most folks are here though. This is a pretty epic day. Oh, somebody's missing. All right. And does everyone have a pin and a roller here?
I've got 2 rollers, actually. No, I'm just joking. I'm just joking.
Oh, Sean, getting way too comfortable in this class. Well, anyway, if you don't have a book and you don't know, just make a note. 8 is a pin and a roller. And also 6. Or 7, sorry. 7 is a pin and a roller. No pin stuff. Good?
Yeah.
All right. We're gonna do 5. 5's extra credit.
Is it?
Absolutely.
Okay, here we go.
It's been a long day. Number 5. 10 points. Extra credit.
And?
If it's beautiful. Oh, come on, 5 small. If you don't have a book, I'm drawing it. It looks symmetrical, yeah? Yeah.
Yeah.
Yes.
Symmetrical in shape, is it symmetrical in load? No, we know. Yeah, it is not. That's a side load coming in. Some kind of wind event. 300 pounds. It's labeled ABC. CP. 30 degrees. Feet. Has a pin at A. And a roller at C. It is extra credit. Which means you gotta work it before I work, it, just so you know. So don't muck anything up.
Extra credit for participation or,
Participation in accuracy.
um.
Gotta get it right. Not for all the extra credit, but for all the extra credit, you gotta get it right. It's like a quiz, right? This is very much what your quiz will look like on Friday. Simpler truss. Find the force in members A, B, B, C, A, D, D, C. You might not have to do them all on the quiz, but we gotta do them all right now.
What's the D going down? What's that?
That is 600 pounds. Time is short too. Not to stress you out.
Thanks, man.
You're welcome. The boss is coming down the hall and would like this. Would like this done. What if the quiz said, what's the force in member BD?
I don't know. Yeah, which. 600.
Exactly. Looking at point D. It's gotta be direct 600, is it compression or tension? Points away from the point here, because this one points away, so this is 600 tension. By observation. We have a clean cross at D. You want to pick those off when you can. And when I find AD, I know it's the same as DC. So I'm gonna get my reactions. They don't give you the height. How do we solve that problem?
I would have we can use tangent, tangent, would be 12 divided by,
It would be
oh,
opposite.
I'm sorry, 12 times 30 tangent.
Yeah, so tangent's opposite over adjacent, so y over 12. So 12 times the tangent 30. Pretty much what you said.
6.9, right?
Yep, 928. So if it's a 10-point problem, half the points are in the reactions. Like that's kind of how I grade it. So on the quiz, like get your reactions, solve them out, do that correctly, that's half the value. And then do your joint analysis. Kick it off. Did I get them right?
I think I got it.
I might have
Wait,
got it
how'd
wrong.
you do Oh, right.
I'll calculate it again. Anybody get my numbers?
Sorry,
Oh, that's a good sign. One made the same mistake. Yep, same number. Pretty good with those numbers. So then, where are we gonna start? I'd probably go with joint C. It's simpler than joint A. Has one less force. I see three forces at C, so how can I solve that?
The Y component of BC.
Yeah, you can do components, which would say, hey, that Y component of BC has to be equal to the 386. What's the other method when I see three forces? Triangle. You can build a triangle and just solve it. So either way, if I do components, what I'm really doing is I'm looking at translational effects in the Y or the X. Either one, Y is the one you'd want to do. BCY comes down, 386 goes up. I don't actually care that you write that out. Like by now, we should, if we're starting to see that those two are equal and opposite, you can just note that BCY equals the 386. It's got it. Now I can go for BC, which is the hypotenuse of this triangle with its components. So could use sine 30 equals BCY 386.6025 over BC. BC equals. This is from this little triangle right there.
But how'd you get the four?
Maybe I got it wrong. I'm rewriting it.
Do like 10?
Yeah, I think I used it wrong.
Are you doing opposite over adjacent?
Yeah, I'm using cosine. So I did not use tangent. So that means I need to use the hypotenuse, which I don't think I did when I calculated this. Let me look. Cosine. Enter times. Yeah, 669. DC is pointing away because BC comes down and over and points in. So BC is right effect, BC's got to be left effect. And if it points away from the point, it's tension. So first I had to understand that BCX and DC are equal because they're the only two X forces, right? And then I use this little triangle right here to get BCX, which is equal to DC. So I use the cosine 30. So here's the 30 right up in here. Cosine is the adjacent side, that's BCX. and divide by the hypotenuse of BC, which was 77320.
It's AD.
Hang on, let me get this one answered. So that gave me BCX, which is equal to DC. Kevin, got it? So yeah, if I know this, I know this. Got it. And if this is intention, this is intention. 669.6 tension. So those T's are really, or crosses are really handy. Because now the only thing I have left to find out is this. AB.
I did that one first.
So you got it. All right, wrap it up. Wrap up AB. Turn it in.
Is AB's the same because it's like the triangles the same?
No, no. This is the same.
Oh.
Because of this point. But since we're got crazy loading 300, I don't know AB. AB, you have to find either at point A or point B. I wouldn't go to point B. I would do point A. Unless you've already done point. So I draw a new one at A, but you know everything. You know AY is 213. The 213 number, you know AX is 300, you know AD is 669. You just don't know this one thing. If you look at forces in the Y component of AB's got to be equal to the 213. So you could just go with that. The 213. So if I look at just this joint, AY is 213. What's the only other Y force? Yeah, the Y component of AB.
In equal A.
Oh, I see, okay.
Yeah, so those gotta be equal and opposite. 30 degrees. I think it's the same on both sides, 30 degrees. So really, joint A comes down just to an analysis of AB. If you see that this Y component is the same here, these two gotta be the same, and it's the 213 number. So 213 for this. Now I got 30 degrees one side, I just need the hypotenuse.